What if the green slime floating in a pond could one day power a jet across the ocean? It sounds ridiculous. Until you realize some of the world's hardest industries are now desperate for liquid fuels that oil cannot, politically or environmentally, provide forever. And hidden inside those microscopic organisms is the same basic promise that made petroleum powerful in the first place: STORED, carbon energy. But this is not the fantasy of turning salad into gasoline. This is a real scientific and industrial race to turn sunlight, water, carbon dioxide, and algae into one of the most valuable substances on Earth. Because if this works at scale, fuel stops being something we only dig up and starts becoming something we grow. And that single shift could rewrite how planes fly, how ships move, and how nations think about energy security. The real surprise is not that algae can become fuel. The real surprise is why that idea still has not taken over the world. Modern civilization runs on dense liquid fuel because dense liquid fuel is brutally convenient. Batteries work beautifully in many places, but they struggle when the machine must carry enormous weight over enormous distance. That is why aviation, shipping, and some heavy transport still cling to molecules, not just electrons. The problem is that the molecules we built the world around came from ancient carbon buried underground. Every time we burn them, we reopen a carbon account that nature closed millions of years ago. So the search began for fuels that could fit into existing engines but come from living systems instead of fossil history. Crops like corn, sugarcane, and soy offered one answer, but they opened a new argument about land, food, and water. That is where algae entered the conversation like an outsider with a very unusual advantage. Unlike traditional fuel crops, many algae species do not need prime farmland to grow. Some can grow in salty water, some can consume concentrated carbon dioxide, and some can accumulate astonishing amounts of oily material inside tiny cells. Scientists have dreamed about energy from algae for decades, long before today's climate urgency made the idea fashionable. The logic was always seductive. Algae grow fast, capture carbon as they grow, and some species naturally make lipids that can be refined into fuel. In theory, it looked like a miracle crop that was not really a crop. In practice, reality was much messier. Growing algae is easy in a beaker. Growing oceans of algae cheaply, cleanly, and consistently is a completely different game. For years, the technology lived in that painful space between scientific possibility and economic frustration. Investors saw promise, then delays. Engineers saw progress, then contamination, energy losses, and stubborn costs. But the dream refused to die, because no one could ignore how perfectly algae seemed to fit the energy puzzle no one else had solved. At the center of the story is a simple biological machine. Algae use sunlight to convert water and carbon dioxide into new biomass. Under the right conditions, some of that biomass becomes oils, carbohydrates, and proteins that can be separated and upgraded. The oils are the part most people imagine first, because they can be processed into diesel-like or jet-compatible fuels. But modern researchers increasingly look beyond just the oil. Because if you only chase one valuable molecule, you usually lose the economic battle. So the smartest strategy is often a full algae biorefinery, where fuels are made alongside chemicals, materials, feed ingredients, or other high-value outputs. That means the future of algae fuel may depend on not treating algae as a fuel crop at all. It may depend on treating algae as an entire platform industry. And that changes everything about how the business case is built. To make algae fuel, you first need to grow extraordinary amounts of living material. One option is open ponds, where shallow green water sits under the sun in huge engineered loops. They are relatively simple and potentially cheaper, but they are exposed to weather, evaporation, and contamination. Another option is closed photobioreactors, where algae grow inside transparent tubes or panels with tightly controlled conditions. These systems can be more precise, but precision has a price. Then comes harvesting, which sounds harmless until you remember the algae are suspended in massive volumes of water, separating tiny cells from all that liquid can consume energy, money, and patience at industrial scale. After that, the biomass must be broken down, extracted, and upgraded into a fuel that meets strict performance standards. And every stage silently asks the same brutal question: are you gaining more value than you are spending? That is why algae fuel is not just a biology problem. It is a systems engineering problem disguised as a green dream. Even so, the sectors watching this most closely are the ones with the fewest easy alternatives. Aircraft cannot casually swap liquid fuel for something bulky and weak. Ships crossing oceans need energy that remains stable, dense, and globally transportable. That is exactly why sustainable fuel demand is rising fastest in parts of transport that are hardest to electrify. Algae-based fuels are therefore not competing with the easiest energy transition. They are targeting the most difficult one, and that gives the technology a strange kind of strategic power. A fuel does not need to dominate every car on Earth to become extremely important. It only needs to solve the problem nobody else can solve cheaply enough. That is where algae still has a shot. Over the years, algae has attracted headlines because the numbers can look almost unbelievable on paper. Fast growth, high productivity potential, non-arable land use, saltwater options, carbon dioxide utilization. It is the kind of list that makes governments, startups, and media all lean forward at the same time. But the algae story has also been damaged by overpromising, because potential yield on paper is not the same as profitable output in the field. The history of this technology is full of moments when excitement outran infrastructure. That does not make the science fake. It makes the scaling challenge brutally real. The first obstacle is economics. If algae fuel costs far more than conventional fuel, adoption stays trapped in pilot projects and niche demonstrations. The second obstacle is energy balance, because a green feedstock loses its magic if processing it devours too much energy. The third obstacle is biological unpredictability. Living systems can mutate, crash, contaminate, or simply behave differently when the weather changes. The fourth obstacle is infrastructure, because a promising fuel still needs refining pathways, certification, logistics, and buyers. And the fifth obstacle is patience. Energy transitions often reward technologies that survive disappointment longer than their critics expect. Algae may still be in that test of endurance right now. Yet, the world keeps returning to this idea because the need never went away. We still need cleaner, liquid fuels for planes, ships, and industries that cannot simply plug into a wall. We still need ways to produce energy from carbon that is already moving through the living world. Not just carbon extracted from ancient geology. We still need systems that can work with sunlight, industrial emissions, difficult land, and harsh water conditions. So maybe the strangest part of algae fuel is this: the pond scum story was never really about slime, but about whether civilization can learn to grow the molecules it once believed it had to dig from the dead.